So far, we discussed work done by a constant force. The force does not change with time. And only then will our simple definition of work will work. Now, what is the simple definition of work? Work done equal to force multiplied by the displacement. This will work only if this force remains a constant. Now, very often, the force may not remain a constant. For example, I want to stretch this spring. Now, if I want to stretch a spring, if I apply a force on the spring will stretch. If I want to stretch it more, I need to apply a greater force. See that? Now, what you notice here, that the amount of stretch is proportional to the stretching force. Do you notice that? If I apply a greater force, the stretch will be greater. In other words, the force here varies with the displacement. Greater the displacement, greater is the force. I can write it like this. Force is directly proportional to the displacement. Well, here the force does not remain a constant. Force varies when the displacement varies. So we cannot use the simple concept. But we can actually extrapolate the result from here into the case where the force remains or the force varies. Now, what will be, in the first case, what will be the shape of a graph of force against displacement? If I draw a graph of force on the vertical axis and displacement on the horizontal axis. In the first case, when the force remains a constant, means the force will be a horizontal line. Now, what is the area enclosed by this graph with the displacement axis? What is this area? Well, the length of this rectangle is x and the width of the rectangle is f, is that right? And so the area of this rectangle is f multiplied by x, which is a measure of the work done. Now, this is actually a general result. If you draw a graph of force versus displacement and you measure the area under that graph, that will be a measure of the work done by that force. Now, can you extend that in this case? Yes, actually, you can extend that in all such cases, and we will talk about that as we move on. If the force F continuously changes, you could probably get a graph like this. Displacement, force against displacement. Now, we have a neat way to interpret this. Now, consider a small displacement ds here, and when the displacement is very small, we can imagine during that displacement that the force F will remain a constant. And therefore, the work done for this very small displacement can be written as dW equal to force, this force multiplied by that small displacement. And we can do that all over under this graph, and then add up all those small dW's. That will give you the work done. In other words, simply stated, no matter how the force changes with time, if you have the graph of force versus displacement, the area under that graph will be a measure of the work done. I want you to understand that concept. No matter how the force changes with time, whether it remains a constant or whether the force changes with time, if there is a graph available with force on the vertical axis and displacement on the horizontal axis, the area enclosed by that graph with the horizontal axis will be a measure of the work done. We will use that as we move on. It becomes more appropriate in calculating the work done in such a case. If the displacement now takes place from S1 to S2, then I can write W equal to integral S1 to S2 of FdS. FdS is the small work done in that very small interval of displacement. Well, integral simply means add up all such work done. Add up all such dWs. Isn't this our dW, the work done during that small interval? So add up all such dWs, that is a measure of the integral. And of course the integral represents the area under the function graph. So this is a measure of the area under the graph measured from S1 to S2. Areas where we will consider force varies with displacement is actually the case of a spring. Alright, let's consider a spring. The figure shows a spring fixed to a support. And if you want to compress that spring, you need to apply force. A force F applied at the free end compresses the spring by a distance dx. So let this force be x, and as a result of that x, the spring now gets compressed by a distance dx. You can see this force compressed this spring by a distance dx. Now, in order to compress the spring further, we need to actually increase the force. That means as the compression increases, the force needed to compress it further needs to be greater. Now, how do you write that? A greater displacement x requires a greater force F. And that means we say the force F is proportional to the displacement x. Now, whether the spring is compressed or stretched, this is the same case. If I want to stretch a spring, if I want to stretch it more, I should be applying more force. I increase the force in order to increase the stretch. The amount of stretch is proportional to the force, or the stretch is proportional to the force. Now, how do you write that mathematically? The stretching force is directly proportional to the force. F is directly proportional to x. And the proportional sign can now be replaced by an equal sign. F equal to kx. Now, this is called Hooke's law, where a spring, when applied either a compressing force or a stretching force, the amount of force is proportional to the amount of stretch, or F equal to kx. This constant is called the spring constant. So, tell me now, if I want to draw a graph of F on the vertical axis and x on the horizontal axis, what kind of graph will that be? Well, that graph will look like this. If I draw a graph of the force F on the vertical axis and displacement on the horizontal axis, it will be a straight line through the origin. Now what will be the slope of this graph? The slope of this graph will be K, the spring constant. Alright, now tell me, if I measure the area under this graph, what will that area give me? The area under the graph will give me the work done by this force in producing a certain displacement x. Alright, let's measure that area. Suppose the displacement is x up to here, and we say this is my displacement x. That means this area is a measure of the work done. Work done therefore is, can you write what that will be? What is the area of this figure? Area under this graph. This is a triangle. The area is 1/2 base multiplied by the height. What is the base of this triangle? It's the displacement x. What is the height? Height is the force. So work done is given by the area enclosed by the graph of f against x. And that will be the area of the triangle. That will be 1/2 base times the force F. Alright, help me rewrite this. This F, if you know, is given by the Hooke's law, F equal to Kx. So in here, I'm going to replace that F by Kx. And let's see what the equation now becomes. That will be 1/2 x times Kx. And that will be 1/2 Kx squared. A very important relation. In the case of a spring, if you want to stretch the spring by an amount x, the amount of work done is W equal to 1/2 Kx squared. Alright, so if I want to stretch this spring, now this is the length of the spring when it is not applied any external force. If I now apply a force on it, I'm going to stretch this by suspending this weight from there. Now tell me, what is the stretching force if I suspend this mass? The stretching force will be mg. I have now produced an amount of stretch x. Now look at this. This is the length when it is unstretched. Now I can measure the length x, and therefore I can now calculate the work done in producing the stretch. What is the work done? Equal to 1/2 Kx squared, where K is called the spring constant of the spring, and X is the amount of stretch. Okay, tell me, what is the unit for measuring the spring constant? K. K will be measured, if you solve for K, you can see K equal to F over X. That would be Newton per meter. K is Newton per meter. It is a measure of the amount of force that is needed to stretch the spring by 1 meter. That is the value of K. Suppose I say the value of K for this spring is 30 Newton per meter. It means if you want to stretch this by 1 meter, I need to apply a force of 30 Newton. That is the meaning there. So what this shows is that the work done in stretching a spring by a distance x equal to 1/2 Kx squared. The work done in stretching or compressing, both remains the same. So let's recap this one more time. If a force